Hello, everyone, and welcome back. I would like to introduce to you Dr. Bruce Kramer. He is the Program Director and Senior Advisor for the National Science Foundation. And sorry for the delay, but he is just joining us from the World Manufacturing Forum being held simultaneously in Cernobbio, Italy. Dr. Kramer is an MIT graduate, and he has served on the faculties of mechanical engineering at MIT and George Washington University. Currently, he's a senior advisor at the National Science Foundation, coordinating NSF's participation in the National Advanced Manufacturing Program. This morning, he's going to be giving us a visionary look at Industry 4.0. And Dr. Kramer certainly knows something about vision in industry. He co-founded Zoom Telephonics of Boston, a NASDAQ company and producer of communications products marketed under the Zoom and the Motorola brands. He holds 3 U.S. patents and is a fellow at the SME and an international fellow of the School of Engineering of the University of Tokyo. He's received numerous awards for manufacturing research, as well as the Distinguished Service Award, which is the highest honorary award granted by the National Science Foundation. Please join me in welcoming Dr. Bruce Kramer to the World Manufacturing Forum North America. Welcome.
Thank you, Teresa. It's a pleasure to be here, and thank you for that kind introduction. I'm going to talk to you a little today about maybe a slightly alternative view of the future of Industry 4.0. And the purpose of it is to encourage the community to think a little more outside the box and about what the possibilities may be. Part of the reason for that is that the current efforts in digital manufacturing concentrate on improving the efficiency of large manufacturing companies. There's nothing wrong with this. Large manufacturing companies have the resources to invest in new technology. But there's a contrast between those problems and that approach and the digital transformations that have occurred in other industries, where, in general, the tools that are used evolved from the bottom up. Take, for instance, the case of Amazon. Amazon took the simplest problem on first, selling books. Books are all stored in somebody else's warehouse. They're all the same shape. The warehouses are more than happy to drop ship them for you if you've got orders. It's a very simple retailing problem. And from that start, Amazon evolved to the point where it is now the world leader in retailing, warehousing, and logistics. So, question I pose is, would a retailing 4.0 program analogous to the Industry 4.0 program have given us Amazon? And I want to leave you with that question as I proceed. As Teresa said, I'm from the National Science Foundation. National Science Foundation is an independent agency of the executive branch of the federal government. It's the second largest independent agency after the National Aeronautics and Space Administration. Franklin Roosevelt was persuaded by his science advisor, Vannevar Bush, during World War II, that the great advances of the war effort that were produced by the science and engineering research community could be perpetuated in peacetime for the benefit of the country. And Bush, who I think was a genius of sorts, came up with a structure of a national foundation that could make that happen, and that is the National Science Foundation. We don't really have a direct highway into the president's office. We mostly interface to the executive office through the Office of Science and Technology Policy, and that's got an advantage in that it takes us more or less out of the political process, but it's also a disadvantage because we don't have a cabinet officer sitting right with the president at those cabinet meetings, bringing forth our agenda. I want to bring to your attention that we have a future manufacturing solicitation. This was run for the first time in 2020, just concluded. It's NSF-wide. It's got all of the directorates of the NSF involved except geoscience. Last year, we made 24 awards totaling over $40 million. The thrust areas are biomanufacturing, cyber manufacturing, eco-manufacturing. And it's very likely, almost a certainty, that we'll have a similar solicitation in 2021. It should be announced within the next couple of months. And I want you to keep it in mind because we'd like great teams, university industry teams, to propose to this opportunity. NSF currently provides over $8 billion a year in funding to U.S. colleges and universities and small businesses. Many of those small business projects are spin-offs from U.S. colleges and universities. And we'd love to see some proposals on new ideas for the future of manufacturing and the future of Industry 4.0. Sometimes these projects work out spectacularly well. There are lots of creative people in U.S. universities, and if you let them think about what the future is, sometimes they invent the future for you. This is probably our biggest success story. It's a final report from the Stanford Integrated Digital Library Project. NSF, DARPA, and NASA came together in 1994 to launch the digital digital library initiative, and 6 digital library projects were funded. These were relatively large projects in the range of $4 to $5 million, which is big for us. And those of those 6 projects, 5 were essentially information repositories with digital card catalogs that were curated by information scientists, traditional digital libraries. They computerized the old methods, and to be kind, they were modest successes. Stanford, in contrast, threw away the card catalog and the search methods used by the information scientists and enabled the web-based economy that we enjoy today and which is a pillar of our economy. We need some of that bold thinking in manufacturing. And you can see this is the final report. You can see that Larry Page was a graduate student on the project and that he worked for 160 hours or more on the project. Sergey Brin was an NSF fellow, so he didn't have to report his time. You know, we take Google for granted now, but there were a lot of potential objections to Google's approach to digital libraries at that time. In particular, it takes a lot of expertise to be an information scientist. It's very complicated. How could we possibly do it without that expertise? But Google understands nothing about what's on the web pages it finds. It uses none of the techniques that information scientists use. There were potential intellectual property problems. Many of the existing works were copyrights. There were not a whole lot of web pages on the web in 1994, but it was easy to start with libraries because in some ways the stakes were low. More serious issues must be considered in manufacturing, but it's pretty much the same set of issues. And I want to make it clear on the bottom that in time, all of these problems were more or less overcome. And we shouldn't estimate the power of the capitalist system, which manages to work out these issues once there's money that starts to be made. Once there's a potential profit motive, many of these problems go away. And Google was able, as it grew, to harvest the expertise of a broad community that had varying degrees of expertise, a vast universe of new free content involved. It's not exactly free, but an advertising model made it possible for that content to grow. And pay for copyrighted material was even achieved. And, you know, Napster came and went, and we now have a pay for content model that's working very effectively in the marketplace. So we need the same kind of thinking in manufacturing. We need to think of new ideas that might have huge differences by doing things in different ways. One advantage of Google that it was, again, it was an application in which network tools could evolve from the bottom up. Manufacturing is more complicated. Large manufacturers need top-down control of their supply chains. Uh, they're risk averse. They tend to be late adopters of proven tools, not early adopters of new tools. And the same was true in the retailing sector. Walmart was not the first to adopt the new tools. Walmart and its compatriots were the last to involve the new tools once they were proven and known to work. Small users were the early adopters of those tools. They would tolerate the glitches in the system because it enabled them to get into business where they couldn't get into business before, reach customers when they had no way to reach customers before. So this is more analogous to our small and medium-sized manufacturers who have very limited ability to reach out into the U.S. economy at large, to reach entrepreneurs, to reach people who need things made and who want to get into business. In general, today, they're forced to go to China, to go to Shenzhen, where they can sit down at a table and get access to the manufacturing services that they need. But if you draw an analogy to the web-based network that we enjoy today in most other industries, that might be possible in manufacturing. Even large companies lack in-house manufacturing expertise. There was a story that hit the newspapers a while ago of Apple's attempts to establish manufacturing capabilities in Austin, Texas. And the story was that Apple had a very specialized screw that they needed for the iPhone, and that they went to a local manufacturer in Austin, and that manufacturer was unable to produce the screw in the quantities that they needed. In fact, it fell far short. But in truth, there were many, probably hundreds of manufacturers in the United States who could have produced that screw. But even Apple's in-house manufacturing expertise did not give them a sufficient understanding of what was required to produce that screw to locate the fabricators who could have done it for them. So this is a pervasive problem. So why not start to try to look at something new? Why not try to see if we can't get a self-sustaining evolution of a digital manufacturing marketplace started? And it's encouraging that again, uh, once companies start making money using the tools, they evolve very quickly. I was surprised to see that within a period of 5 years, we had moved from Mosaic, Lycos, and Front Page to Internet Explorer, Google, and a situation where Microsoft Word could create a web page for you with no HTML coding whatsoever. I want to remind you that before Mosaic, Yahoo was a directory of Jerry Yang's favorite web pages. Nobody could find a web page. They were passed around from user to user in a very inefficient way. Uh, I'm not denigrating what we're doing in Industry 4.0 in any way. There are great tools and they're being applied, but it's not economical for many manufacturers to put in the development effort that's required, and as a result, the adoption rate has been very slow. I heard this phrase last week, and I loved it. Proof of concept purgatory. To date, we've largely been doing very expensive demonstrations in the hope that generalizable principles would emerge that would make it less expensive to implement these new technologies. It's not that we haven't made progress. We've come to the point where almost any process can be controlled, but every new application is a new development project. And often, either new applications that seem very similar to the old ones are development projects as well. The learning curve is very steep and the cost comes down very slowly. And as a result, these applications are cost effective only for the most expensive or high volume products. If you're making microprocessor chips, and you've got wafers with hundreds of chips on the wafer, and you're putting them in a CVD furnace to perform the next process step. And if the process doesn't work, you're going to ruin $5 million worth of wafers. You can get a couple of PhDs to spend the time and money to get that process under control. But if you're not in a situation of a very expensive product, you can't really justify that time and expense. Workforce training may help, and it's important, and we should do it, but keep in mind that it only helps to the limited extent that a capable technician costs less than an experienced engineer. That's a factor of several times, but it's not going to get you to the point of widespread usage, if we can draw the analogy again to the internet marketplace, which essentially requires no capital costs to engage in the marketplace. So again, I'm urging the community to think about questioning the old beliefs, questioning the old assumptions. And I'm going to offer you two examples. These are just examples. We want your proposals with better ideas. There's nothing magic about these. They're just what I could come up with. All right, let's look at the current approaches to manufacturing process control. There are really only two problems in manufacturing. The first is reliable process control. The second is or ensuring that the process executes with zero problems. The second is the translation of design information to manufacturing procedures, and again in a trouble-free way. In process control, the analytical models that we use, they can be developed, but they lack generality. They're very narrow, and they're hard to apply to new, similar situations. Machine learning, in contrast, it promises generality. It's largely unproven, but machine learning uses access to enormous amounts of data. On the other hand, the industrial culture demands secrecy, and few companies generate enough data on their own to effectively train a machine learning system. So if the analytical physics-based models have been slow to provide the cost savings that are needed, if machine learning holds the promise of the future, but secrecy stands in the way of providing the data access and the confidentiality to make companies feel comfortable sharing their data. In design to manufacturing translation, we've been stuck on the generative model, which builds manufacturing expertise of experts into the software that's used by non-experts. One thing that we've avoided or we've not taken advantage of is the embodied expertise that's embedded in all of the parts that have been designed and all of the parts that have been manufactured by design and manufacturing experts. All right, how can we aggregate data across manufacturers? And again, the challenge is to accelerate the development and effectiveness of artificial intelligence and machine learning. Manufacturing generates more data than any other industry, including the financial sector. It has great problems for world-class machine learning researchers to work on. And essentially none of those world-class experts in machine learning are engaged in manufacturing at this time. Industry, again, can play a key role in motivating the involvement of those experts. And one step that's being taken is the National Science and Technology Council subcommittees on advanced manufacturing and artificial intelligence and machine learning are holding an upcoming set of 3 joint symposiums on AI and manufacturing. The first one will be held next month, and the reports of these symposiums will be available to the public. We're hoping that many new ideas will come out of the symposium, but possible ways to enable that kind of data sharing would be new encryption tools, possibly a model in which the vendors own the data that comes from their machines. This model is beginning to emerge. Aggregators of data may emerge who pay manufacturers for their data and then market the services that are developed using that data. There might be trusted aggregators who pool data. This could be might be big users or government users, or possibly industries such as CAD vendors who already keep large data sets of designs confidential, and they're trusted in doing that. And standards can play a role. The European Commission is beginning to investigate this, and we can anticipate some interesting ideas coming out of that process. I talked about generative design. We've been working on the path of building manufacturing expertise into software almost since the dawn of the digital age. The generative model assumes that every design emerges full-blown from a blank CAD system. So we start with a blank screen and we begin the design. There are unstated assumptions in the generative model. The first is that what I just said, that the design emerges de novo, based on the specifications, the analysis tools, and the knowledge and the creativity of the designer. The second is that a manufacturer will make anything that is in the capabilities of their plant. So if we could just find a manufacturer who has the tools and the equipment to produce the design that we want, we can approach that manufacturer and they will make that for us. The fact is that the starting point for most designs is a previous design. Almost everything has been manufactured before or something close to it. All of the problems in producing that part have been solved by someone, somehow. It would be very powerful if we had a way to find those similar parts, even within a company. Most companies can't even find the parts that are similar that they have produced themselves. The second assumption is also not true. Most manufacturers specialize in producing a limited class of parts in parametric variations. The entrepreneur who wants to get into production, the most desirable for that entrepreneur is to find a manufacturer who is producing that part class already, because that manufacturer has a tremendous amount of expertise and can provide the part at relatively modest cost to the customer, but a relatively good profit margin for the producer. There are no problems that need to be solved. And to pursue the digital library analogy, there are billions of proven designs that already exist and could be made available if we could make the manufacturers feel comfortable doing that. Just by way of illustration, I don't know how many of you listen to Shark Tank, but how many times have you seen entrepreneurs give up 1/3 of their company because Lori knows a manufacturer in Shenzhen who can produce the product? We need a digital Shenzhen in the United States, a digital marketplace that makes it possible for entrepreneurs to find the right manufacturers who can get them into business. There are a lot of advantages to this. That library of parts that's already been produced incorporates all the design expertise of the millions of designers who design them. It includes all the manufacturing expertise of the millions of manufacturing engineers who solved all of the problems that were needed to be solved to produce them. Many, if not most of those parts have probably been tested in service. They've already been proven designs. They can be provided to new customers at low cost with a high profit margin. And they are all co-located with the domain experts. Those domain experts, if they can't make the part, probably know somebody who can. If the design isn't quite right, they can probably tell you what's wrong with the design. It's extraordinarily valuable to small and medium-sized businesses trying to get in production. In addition, each part comes with a detailed geometrical representation, a debugged process plan, both NC code, and a set of tools, cutting speeds, fixtures, quality control procedures that go along with it, a manufacturer with the associated expertise, and maybe most importantly, there's no need for that manufacturer to disclose any proprietary information about its manufacturer to the customer. If there's a secret sauce involved, the customer doesn't need or probably want to know that. The major stumbling block is that IP protection for CAD models may be an issue. But I think it's an open question how big an issue it will be. In particular, it's likely that the parts with the least IP will be the most in demand. Nobody is going to get into a business making jet turbine blades to go into competition with General Electric. Those designs are probably probably of interest only to industrial spies. Even better, a number of companies are already in the part search space. These 5 companies all have versions of products. They're incipient versions, but they're quite functional, and they might be good enough to get a marketplace started. Most of these tools now are deployed to search within company or in a curated collection of designs or catalogs that's maintained by the companies themselves. I want to ask you whether this sounds familiar. It sounds a lot like the Digital Library Project. We've barely gotten to the library phase, and there's vast opportunity to move beyond that. There are also universities working on search tools. There's a group at Rutgers and Georgia Tech working on generalizing the 2D facial recognition algorithms to recognize 3D CAD models in similar ways. There's a group at Iowa State that's generalizing 2D image recognition algorithms to voxelized 3D CAD models. These methods, early results are saying that a 3D CAD model has too many voxels to use image recognition or volume recognition in an effective way in a reasonable time. But I want to point out that voxelized 3D CAD models should be highly compressible. They're mainly strings of empty space concatenated with strings of filled space. And experts in compression could be interested to develop homomorphic compression algorithms for compressing these 3D models while maintaining the shape information that's needed. We've not received a proposal yet, but I would very much like to receive a proposal along these lines. There's a third group at NYU and University of Delaware that's developing methods of converting 3D CAD files to one-dimensional signals that can be identified using signal processing techniques. And remarkably, these 1D signals are reversible. You can take the signal that's produced and recreate the CAD file, so no information is lost. So what I'm aiming at is a searchable web of CAD models uploaded by the manufacturers themselves that represent what they're capable of. And in the ideal case, these CAD models would be web crawled and indexed just as Google web crawls and indexed web pages, so that they would be searchable by web search tools and provide a prioritized list of possible parts that have already been produced that might be suitable for or adaptable to the needs of potential customers. So if we look at the requirements for such a marketplace, on the web page side, we need what looks like a CAD model with adjustable parameters that can be selected by the vendor and set by the customer. So the vendor would specify that this dimension of the part could be varied between these limits based on the available capabilities of the production facility. The customer would have a text box or a slider that would allow the desired parameters to be set, and a tool like this is probably within the capabilities of most of the CAD vendors that we know today. So that's probably under control. For the browser, we can probably use our current browsers for this purpose. The search engine, as I said, there are rudimentary search engines that are available that could be tried. And the remaining problem is whether manufacturers will be willing to make their CAD models accessible. But I want to take you back to the digital libraries. Those copyright issues were solved when there was enough usage of the system that vendors of information or sellers of products could make a profit using the system, and that might work very well even in the manufacturing context. I want to close by reminding you that we have a $40 million solicitation that is coming up. We'd like to see proposals with promising out-of-the-box ideas for taking Industry 4.0 in new directions. We're not particularly interested in financing the next demo that doesn't apply broadly to a future in which Industry 4.0 is more accessible and accessible at lower cost. Ideally, these proposals should come from university teams, but industry should play an active role in assembling those academic teams. In general, industry knows who the university researchers who have good capabilities and good vision for the future are, and they can encourage those researchers to come together into teams. And we encourage university teams to do the converse of that, to reach out to industrial companies that have capabilities that are needed in order to make progress on this research, to bring them into the fold, to value them as collaborators, and to take advantage of the capabilities that industry has that are needed by the universities. So with that, I thank you very much, and I'd be happy to take a question if there is one.
Yes, Bruce, thank you so much for sharing that information on the vision. I have a question that popped up. It says, Bruce, does the strategy of Manuvation 4.0 of letting industry define the most important requirements and focus on the Industry 4.0 technologies and gaps that hit the mark rather than try to boil the ocean?
Well, I think we have to concentrate on the gaps, but I would add to that formulation that we should identify the gaps in which fundamental rethinking of the way we implement the tools that we're using can allow those tools to be applied to a much broader range of applications than they can be applied to today. And that is probably the only effective way to drive the cost down, and driving the cost down is the only effective way to penetrate to the medium and small-sized companies who desperately need these technologies.
Do you think that this is going to, they're kind of worrying about overwhelming SMEs with Industry 4.0. What are your thoughts on that?
Well, I think we shouldn't overwhelm them. I think the current methods and tools that we use they're really not ready for the small and medium-sized manufacturers. We have taken the approach that if we trained workers better, they could make more effective use of the tools that we have, and that is certainly true. But I think there's a long way to go in driving the time and cost and expertise needed to apply the tools down. And unfortunately, that is a research problem. That's for America's colleges and universities, where there are lots of bright young people who can accept the funding that NSF makes available, to think outside the box with no pressure of profit and delivery schedules, to come up with new ideas that let us reach across many applications and develop sort of a higher level set of tools that can be applied more broadly.
Excellent. Thank you so very much for sharing the information with us today. We look forward to more innovations as we go through this. So thank you so much, Dr. Kramer.
It's been a great pleasure for me, and I'm very happy to have been able to do this.
Our pleasure as well. Thank you.
All right. Thank you.